Here we have one more example. Let's say we have the same problem. Hopefully I can get the pen. Draw here. Have same problem. This is a beam with Young module of elasticity and length L, and let's say you have a couple moment M0 at the tip, and this is welded to the wall. Now we want to find the equation of the elastic curve after deflection. Obviously this is going to go down like that. In particular, we want to find the deflection at V at XL. Alright, to solve this problem, we go back to the equations that we derived in class. Let's use back. The equation that we derived in the class was the second derivative of V is equal to m over EI. Because this beam has constant cross section, let's say for example cross section is like this, then the I is just constant and is not a function of x. Similarly for E, it's made of same material with constant modulo of elasticity. So I can just take this EI out of the integration to simplify my job. That means that I can write this equation like dEI is equal to E2 EX2 equal to mx. All I did, I just brought the EI to the left side, and then I have my couple moment, my moment diagram. So the boundary conditions for that is V at x0 is 0, dV dx x0 is equal to 0. So this is my problem, which is an ordinary differential equation of second order with two boundary conditions. This is a mathematical description of problem. Okay, and I know that dV dx is equal to theta is equal to a slope at wall, the slope of the elastic curve. We already discussed this. Alright, so let's go ahead and do the first step. The first step is to get my mx, to plug it in, double integrate, apply the boundary condition, get the equation of elastic curve, and then you can evaluate it at x is equal to L. So let's go ahead. If I want to get my moment, I can cut this. I can take my x from the left, like always I did. But when I cut it, I can take the right part as my system. Doing so, I get, this is my system. That's my m. At x, there are Vx, Nx, shear, internal shear load and internal normal load or axial load, but because I don't have shear or axial, I just forget it, right? So you only have mx right here, and then there is a m0. Look, this problem, everything is parametric. So we don't set M0 EL, we want to find the formula. And that's all, except we need to make a notation from here to here is equal to, this is the important part, L minus X. Okay, so then I'm going to write the summation of moment about any point x, 0. Any point, I pick point x. That means if I expand this equation, I get mx with a negative sign, negative m0 is equal to 0. That means moment at any x is equal to negative m0. So if I want to draw the moment diagram, I simply, if I draw it here, let's use another color, like this. So the moment diagram is simply, if this is x, moment versus x is simply a negative number from beginning to the end, and is equal to negative m0. This is internal moment diagram. So let's go ahead and plug this negative m0 into this equation that I'm showing it with a star. So I have ei second derivative of v with respect to x is equal to negative m0. Go ahead and do the first integration. You get ei dv dx is equal to negative m0x plus the first constant of integration, c1. Now you can apply this boundary condition right here. As you can see, I'm circling it. It says the derivative at x0 is 0. So let's plug in this condition, ei, the derivative, let's put x0. This is equal to negative m0 times 0, because x is 0 plus c1, and this should be equal to 0. That means that c1 is equal to 0. So far, my equation, if you go back to this equation, my equation is ei dv dx is equal to negative m0 x, because c1 is 0. Go ahead and do the second integration. So if you integrate both sides one more time, then you get ei dv d, sorry, where is my eraser? Ei v, which means v of x, because this is also a function of x, but for simplicity I just don't write it to make it shorter, is equal to negative m0 x squared over 2 plus c2. Now if you take the derivative of both sides, you get the equation above, right? ei dv dx is equal to negative m0 x plus 0. Now apply the second boundary condition. The second boundary condition is v at x0, or deflection at wall, is equal to 0. If I apply that, I get ei v. All I do, I'm just evaluate this equation at x0, right? So ei v at x is equal to 0 is equal to negative m0 0 squared over 2 plus c2. This should be equal to 0. That means immediately c2 must be 0. Okay, so the equation of elastic curve is ei v of x, just put c2 0 here and you get the final answer. Ei v of x is equal to negative m0 over 2 x squared. So that's the equation of elastic curve. So I can bring this ei to, let's put this ei right here. So instead of doing that, I say 2 times ei goes to the bottom, and I can just get rid of this extra information. So now let's evaluate this at L. So at x is equal to L, the value of deflection, v at x is equal to L, is equal to negative m0 over 2 ei times L squared. As you can see, the value of m0 is a positive number, the value of L is positive, a square is always positive, so this is also positive. E is positive, I is always positive. And then the end result is multiplied by a negative sign here, so the end result is negative. that simply means down. Now going back to the physics, here I see that, look at here, this distance, you see when I apply a couple moment like that, this should go down, which this actually satisfies the physics. Alright, in the next example I'm going to solve one example that you have a more complicated boundary condition than a simple wall.